In this lesson, we will be learning about the equilibrium constant. We will learn about the how to derive the equation and how to use it. So first, equilibrium. First, you know what the word equilibrium means, and constant means it's no longer changing. So I showed you in the very first slide that K equilibrium, this is the equilibrium constant, and it's nothing more than the ratio of the amount of products over reactants. So here the K equilibrium, or the equilibrium constant, is 10 over 2, or 5 over 1, or 5. The equilibrium constant is 5. Okay? The importance of it is the bigger the number, the more products you have when the reaction is finished. Okay? So let's see how it is derived. So first, let's look at this reaction. It's the same thing, the N2O4 to NO2. Again, you have a double arrow. This is the rate going forward. So the rate going forward, the rate law would be Kf of N2O4. And the molarity of N2O4 is an elementary reaction, so you can use the coefficient as the exponent, one there. Now let's do the rate law for the reverse reaction. Reverse reaction is going down. We're going to call the rate law Kf. So we're going to start with NO2. So it's going to be not F, Kr for reverse. R for reverse. And F for forward. Okay, so R for reverse. And we're starting with NO2 going backwards. So we're going to write NO2. And it's going to be a square there. Okay, so those are the rate laws going forward and going backward. At equilibrium, the forward rate equals the reverse rate. So rate forward equals the rate reverse. The rate forward is equal to Kf N2O4. It's right here. Okay, so we're going to write that here. Kf N2O4 K reverse is right here. We write that here. K reverse R is equal to NO2 squared. Okay. Rewriting this becomes, we're going to put the K's to one side. So now we're going to divide the Kr on both sides. So the Kr goes here. Okay, divide Kr on both sides. So this cancels. Okay. Now we're going to divide N2O4 and put it on the other side. So now we have NO2 squared. And we're putting N2O4 on the other side. N2O4. Okay, so this ratio of K forward to K reverse is equal to the equilibrium constant given by K, uppercase K, EQ. And as you can see, K equilibrium is nothing more than the amount of products over here, the products over reactants. So it's nothing more than the ratio of products over reactants. N2O4. So I just derived the equation for you. Pretty simple. Okay, the ratio of the rate constant is a constant. So if these two are constant, then this is constant. That's why they call it rate constant at that temperature. If you change the temperature, you're changing the rate constant. Okay, the certain temperature and the expression. And every time I say the word expression, I mean formula. Okay, the expression or the formula becomes this. I'm not going to rewrite it. It's the same as that and that. Okay? So if you have an equation that's looking like this, all you have to do is put the products, these are the products, over the reactants. Okay? At equilibrium, the expression for this reaction would be, now, if you look at this, it turns into a C. And you're wondering, why is that? That's the same as K equilibrium. Okay? At equilibrium, the concentrations or the molarities are as follows. So if you want to be specific, it could be Kc, Kp if you wanted pressure. In this case, we're using C for concentration, and it's going to be in molarity. Okay, it's products over reactants. So products are over here, so it's going to be C, and the coefficient becomes the exponent. Times, you're not adding those, okay? You're multiplying it. D, and the exponent D. Okay, and then these are the products. Over here are the reactants. So it would be A to the power of whatever A is times B to the power of B. Okay? For example, the equilibrium expression for this would be K equilibrium, or if you're going to use concentration, you can use Kc, either one, is equal to the products, which is NH3, to the power of 2 divided by N2 times, you don't have to put the dot, okay, times H2, 3, to the power of 3. Oops, that's a 3. Okay, so you might wonder, what do I do with this formula? Well, all you can do is you can look in, figure out how much NH3 you make, you plug it in. Let's say it's 10 molar, and then you square it, and then when the reaction is done, of course, you have reached equilibrium. Let's say this is a 5, then you plug it in, 5, and then let's say this is a 1 at equilibrium. It's a 1, and you just to the power of 3, multiply the numbers, you'll get a number, and that is your K equilibrium. And I made these numbers up, okay? Okay, so here are some facts about the equilibrium constant. Okay, here's the equilibrium expression. Again, it's just a formula. The Kc, the equilibrium constant, is just the ratio, products over reactants. Okay, it depends on the stoichiometric relationship. That means it depends on the coefficients up here. It has nothing to do with the mechanism, so I don't care how it got there. All I'm doing is I'm counting how many do I have of each when the reaction's all done. Okay, Kc depends only on the particular reaction and on the temperature. Okay, make sure you don't change the temperature, otherwise you'll change Kc. Kc is independent of the starting concentrations. What that means is this: if I go into the lab and I start the reaction, let's say I start with there's 12 there. Let's say I start with 6 NO2 and I start with 6 N2O4. There's 12 total, okay? And when the reaction's done, I end up with 2 of these and 10 of those. So I end up with 2 of those and 10 of those. Okay, so this is at equilibrium, and these are sealed. So this is at equilibrium. So what's the ratio of products to reactants? The ratio is 2 to 10. I'm sorry, 2 squared to 10. Okay? That's the ratio. What if I start with 6 of this and this? Well, when the reaction proceeds, some of the NO2 will turn into N2O4 until it becomes 2 to 10. If I don't start with 6 and 6, let's say I start with 1 of these and 11 of these. When the reaction's done, I'm still going to end up with 2 to 10. So it doesn't matter how much I start with. In the end, the ratio will always be the same. Okay, that's what this means. Kc is independent of the starting amounts. Okay, I want you to look at this table and analyze what's happening here. Let me just talk about experiment 1. In experiment 1, I started with no N2O4 in my beaker and some NO2s. At equilibrium, I end up with this much N2O4 and this much NO2. Okay, when I plugged into the K equilibrium, I got 0.211. Okay, first I want you to notice what did they do differently in experiment 2, 3, and 4. Also, look at the ratio. What happens? Go ahead and pause the video and look at that. So here it shows that you started with 0, but now you have more. Okay, in the end, your ratio is the same. Here you started with some N2O4 and then this, and in the end, your ratio is the same. So it doesn't matter what you start with, it'll always be the same. Okay, equilibrium can be reached at either direction. That means it'll either go to the right or to the left until it gets to the same ratio. Here, this is showing it graphically. Here, this is H2, so the reaction is N2 plus H2 becomes NH3. Here they're starting with a lot of H2. Here we're starting with not very much H2. Here they're starting with some N2. Here they're starting with none. Okay? But in the end, look at the NH3. It is the same on both diagrams. It doesn't matter what we start with, N2 and H2, or whether we start with NH3. It doesn't matter. We will have the same proportions at equilibrium. Okay, so let's do some practice here. Write the equilibrium expression, Kc, for the following reactions. For letter A, all you have to do, Kc is equal to products, which is O2 to the power of 3 divided by O3 to the power of 2. Pause the video and do B and C. So in letter B, I wrote NaCl to the power of 2, NO to the power of 2, Cl to the power of 1. For C, AgNH32 to the power of 1, because there's a 1 there, power of 1, and this for the power of 2. Products over reactants. Later on, you will learn that when you're writing equilibrium expressions, notice these are all gas and aqueous. If you have a pure solid and pure liquid, you will not include it in the equilibrium expression. Okay, and I will give you a big lecture on that and tell you why, but for now, just don't put those in. A short explanation is the concentrations of solids and liquids don't change. Therefore, they're a part of the constant number. So what do I mean by don't change? If you have a small piece of solid versus a big piece of solid, the concentration per cubic centimeter is the same. The way the atoms are situated in there are the same no matter how big your sample is. Therefore, the molarity is constant, so it goes into here. Okay, more on that later.